You can start.
Okay, okay. Hello everyone. Good morning, good afternoon, and good evening. Thank you to be here. And my name is Wang Wenwei, and I'm glad to share with you some of my new research progresses. And my today's presentation is about air quality prediction with an adaptive gating approach in spatial temporal convolutional network. So, air quality is crucial to public health, and as our cities grow and the industries expand, the air pollution has become a serious issue, which can lead to rising death rates from heart and lung disease. So, accurately forecast air quality is very important for guiding the government actions or the public health management. Uh, since the air pollutants tend to spread across the space, it is important to consider the spatial dependencies between different monitoring stations. And currently, some researchers use graph convolutional networks, which is GCN, to catch the spatial dependencies which have shown promising results in multi-site air pollution forecasting. And then I will show you the challenges that we are facing in this research field. Most existing GCN-based methods use a shared parameter matrix across all nodes, which limits their capacity to adapt to the differences and the dynamic changes between the monitoring stations. And also, the diffusion process of pollutants is influenced by many complex factors like weather and time. So this makes it difficult for these methods to capture such complex dependencies. So there is a need for a spatial dependency extraction model that can adaptively adjust its way of extracting spatial features. That's what we do in the next. So in this section, I will introduce to you our model. Our model consists of three parts. They are graph convolutional layer, and temporal convolutional layer, and the last prediction layer. In the graph convolutional layer, we implemented an adaptive gating mechanism, which allows the model to autonomously determine the weight matrix for extracting the spatial features. And specifically, we set a gating parameter matrix G. It is the function of inputs on each time steps, and which will then be a part of computation of graph convolution. Then the extracted spatial features of each time steps are arranged as the time series and being sent into our temporal convolutional layers to complete the spatial temporal feature fusion. Finally, the spatial temporal feature will be fed into the prediction layer and be converted to our final prediction. Then we go into the experiment. We obtained a real-world data set from the Beijing Ecological and Environmental Monitoring Center, which contains 34 air quality monitoring stations of 8,760 time steps of data, and the air pollutant and each record include pollutants of PM 2.5, SO2, CO, and the O3. And our experiment was conducted on NVIDIA's GPU, and the code was written in PyTorch framework. We selected two types of comparison methods, which are baseline methods and that only extract temporal features, and and the spatial temporal methods that consider both spatial and temporal features. We want our model to predict air quality in different time scales, so we let all methods predict future air quality in 6, 12, 24, and 48 hours. And we choose RMSE and MAE as the evaluation matrix. Well, to show the superiority of graph convolution, we compare our method with baseline methods that don't extract spatial dependencies. And since our model incorporates spatial correlations between multiple monitoring stations, it can achieve superior results compared to those baseline methods. Then, to verify the performance of our adaptive gating mechanism, we also compared our method with recent spatial temporal methods, and you can see that our method outperforms the comparative methods in overall evaluations of RMSE and MAE matrix. And finally, we designed a ablation experiment to verify the contribution of adaptive gating mechanism and our temporal layer. And you can see that our full model outperforms the ablation models in all pollutants across every prediction intervals. And in summary, in this work, we introduced AGTCN, which is air quality forecasting model. And in this model, we implemented an adaptive gating mechanism for dynamically adjustable spatial convolutions. And our experiments on real-world dataset show its strong performance. Okay, so that's all of my today's presentation, and for any questions, please contact my email address, and thank you for your time.
I thank you for your presentation. The next paper ID is 2807. The paper title is Confusion